Hi students, now we'll talk about section 3.1, chapter 3, position and velocity vectors. Okay, look here, if we have x, y, z direction, we need them ordered as the right hand right hand rule. From x, if I move my finger from x to y, then the thumbnail, this finger will direct to the direction. If we have two positions, position 1 and position 2, the house and the school, okay, the house are located by vector r1, the school is located by vector r2. Okay, the first position vector from the origin to to point 1, which is the house, r1 is equal to x1 I hat plus y1 j hat plus z1 k hat. And the second position vector is r2, which is x2 I hat, y2 j hat, and z2 k hat. If we move from point 1 to point 2 and we have been at point number 1 at time t1 and we go to the point number 2, the position number 2, and we arrive there at t2, then we have delta t between the two situations. So we have delta t going through this time. Maybe we have a third position, fourth position, and so on, r3, r4, and so on. We just need to change the name of the components of each vector. It will be x3, y3, z3, and so on. Is that understood? This vector is vector or position vector. Also, this is another position vector. Okay, when we move from the first point to the second point during a period of time, we have speed because we have changed our position during a time. The change in position, the rate. What is the rate in change in position with respect to time? We can take delta r as vector, which is r2 minus r1. How can we do that? By using the components. We have delta x, which is x2 minus x1, because we have r2 minus r1. We need just to do this operation, x2 minus x1, y2 minus y1, z2 minus z1. This is the change in position using the components. Okay, what is the speed in x direction? As we know, the average speed is equal to delta x over delta t. Delta x is known, which is x2 minus x1 over t2 minus t1, which is delta x over delta t. What is the instantaneous velocity or speed? It is the limit when this rate of change, its time limit is 0. It will be dx over dt. And the same for vy and vz. We have the velocity in y direction and the velocity in z direction is dy over dt, dz over dt. Okay? Now, the components x, y, and z tell us about the position vector r, and the components vx, vy, and vz tell us about the velocity vector v for each position or for each moving body. This is the position vector, and this is the motion in this direction. This is v vector. It is not the same as r vector. So we have now r is equal to x I hat, y j hat, z k hat, as we know, and v is equal to vx I hat plus vy j hat plus vz k hat, where we can write v in this view also, which is dr by dt, which is the rate of change in the position with respect to time, which is equal to dx over dt I hat plus dy by dt j hat dz by dt k hat. This is vx, vy, vz. And the magnitude of each vector, as we know using the Pythagorean theorem, the length of the position vector, which is the x component squared plus y component squared plus z component squared under the square root, and the speed, which has no direction, the magnitude or the norm of this speed is equal to vx squared plus vy squared plus vz squared under the square root. Now we need to look to this example. For a moving object with the position vector r as a function of t, we have the three components in the x component, y component, and z component. Each component depends on the time. So x is equal to, x component in this vector is equal to 3t squared in I hat plus 2t squared plus 4t to the 4 j hat plus 100 k hat. It is independent of t. So x of t, y of t, z of t. What is the vector, the velocity vector? Simply, it is the derivative of the position vector. V of t is equal to dr over dt. This is x of t. We need to derive it with respect to t. 3t squared, it will be, its derivative is 6t. It is 2 multiplied by 3. And the power 2 will reduce by 1. It will be 6t I hat plus the derivative of this term is 4t plus 16t cubed in j hat, and the derivative of 100 is 0k hat. We don't have z component for this velocity. For example, now we can find the position and the velocity at any time. For example, at t equal to 0, we need to find the initial velocity and the initial position. What is r at t equal to 0? We just need to put 0 in the place of t. So it will be equal to 3. If we put 0 here, it will be 0. If we put 0 in y component, it will be all 0. And there is no t in the z component. So the position at t equal to 0 is 100, because the x component and the y component are zeros, but we have 100 in k hat, which is altitude, for example, in 100 meters. Also, you need to be careful that by the dimension analysis, 3t squared, we have r, it is a position, it is a length. Then all the term 3t squared is length. So 3 here has a units. Also, all the term, this term is a length. Also, 100 is a length. So if we need to know the dimensions of 2 or 4 or 100 or 3, we can do it. Also, for the velocity, each term has a dimension length over time, which is the unit, because it is velocity. So this unit here is meter per second, meters per second, meter per second. Now the position, it is 100 meter in k hat. What about the velocity at t equal to 0? Okay, we have the velocity vector, it's 6t, and 4t plus 16t cubed in G here. If we put 0 in t, it will be 0 everywhere. Then the initial velocity will be equal to 0 meters per second. And we can do that for any t. We can choose any t and put it in the relations and find the position and the velocity vectors for this example or any other example. Thank you.